Hi, Viniphysics here with the Physics Odyssey channel. So I recently watched a MythBuster episode. It's called Curve a Bullet, and thought the physics was interesting. So I'm going to let them introduce the episode. I'll talk about the physics, and then you can watch their experiment.
So what's with the hardware?
Well, we have a new movie myth that has MythBusters written all over it. And since this movie's come out, we have been inundated with requests to do it. In fact, it is the most requested myth of the year.
You're talking about the movie Wanted, right?
Exactly. And in that movie, a secret society of assassins shares the ability to curve a bullet.
That's right, just with a little bit of a flick of the gun, you can curve the bullet around an obstacle and hit your target.
This should be fun.
Or really dangerous.
Am I gonna play gun too?
What do we got?
When your target's hidden behind a side of pork and Angelina Jolie, what's a secret assassin to do?
Shoot the target.
Well, supposedly, with a swing of the arm and a flick of the wrist, in obligatory action movie slow motion, the bullet curves around the obstacle, saving your bacon.
Okay, so how do you want to test this?
I say we just go for it.
Exactly. I mean, in the
Okay, so there's the introduction. Let's take a look at the physics. So here's the myth. If you take a gun and you move it in this direction and then shoot it as it is moving in that direction, the bullet will curve. Okay, so assume the gun fires here. The hypothesis is that the bullet will curve and land some distance here from the straight scenario. Okay, so can we prove this just using the laws of physics one way or the other? And the answer is yes, and it's actually quite easy to do it. So the first thing I want to do is figure out the time it takes to get from where the bullet is fired to the wall here, where they will project the position of the bullet. Okay, and that can be figured out by multiplying speed times time is equal to distance. Okay, so I'm looking for time, so time is equal to distance divided by speed. Okay, the distances you'll see here in a minute from their experiment is measured to be 40 feet. Okay, and the speed of a bullet coming out of your average pistol is about 1,100 feet per second. So if you divide 40 feet by 1,100 feet per second, you get 0.036 seconds. So again, that's the time it takes to get from the fire point to the projection screen 40 feet away. Okay, so the next thing I want to compute is the velocity it's going to be moving in this direction. Okay, so again, the gun is moved in this direction in a circle, and it's fired at this point. So it does have a velocity in this direction, right? Okay, so that's what I want to figure out. So there's an equation which relates the radius of the circle that the gun moves times the velocity, the angular velocity that it's moving. If you take that product, you get this speed. Okay, it's called the linear velocity. Okay, so I measured this length, or approximated this length from the video to be about 2 feet. Okay, I approximated the rate at which the gun was moving in a circle at about 2 revolutions per second. Okay, but in order to use this equation, this needs to be in radians per second. So I multiplied 2 revolutions per second times 2 pi radians per revolution, and I got 12.5 radians per second. So that's this number here. So when you multiply 2 times 12.5, you get 25 feet per second. So that's velocity in this direction. Okay. So the next question to ask is, okay, given that velocity and given the travel time of 0.036 seconds, how far should it land relative to dead center, right? Okay, so to measure this distance here, I simply multiply the speed that the bullet is moving in this direction, okay, times the time it takes to get from here to here, which is 0.036 seconds, and when I do that, multiply 25 times 0.036, I got 0.95 feet. Okay, that's 10.8 inches. So that's quite a lot of displacement in this direction. Okay, so let's go ahead and put 10.8 inches. Okay, so this was calculated based on my best estimate as to how fast the gun was rotating, this distance here from the rotation axis to the position of the gun, as well as taking the average speed of a bullet as it leaves the gun for a pistol. Okay, but I wanted to compute an extreme value. What would the smallest, what might be the smallest it would displace in this direction? Well, the smallest displacement would be for a gun that would fire a bullet at a really, really high speed. So the fastest bullet to leave a pistol that I could find online was 4,000 feet per second. Okay, at 4,000 feet per second, it would make it from here to here in 0.01 seconds. Okay, the other thing I assumed was instead of this thing being 2 feet, I assumed it would be 1. And then I also assumed it'd be rotating instead of 2 revolutions per second, it would be moving at 1 revolution per second. Okay, so that would all contribute to give me the lowest possible displacement as kind of an extreme value. Okay, so when I measured the extreme value, I got 6.28 feet per second in this direction, travel time of 0.01 seconds, and I got 0.06 feet or 0.72 inches. So at the very least, the bullet should have been displaced by about three quarters of an inch. And the MythBusters did mention that they could measure a displacement as little as 1/4 of an inch. Okay, so that's the physics. Let me let you watch their experiment, and then I'll come back and we can talk a bit more.
We need a completely controlled environment to test our crazy gunslinging rig, so we've come down to the South San Francisco Police Department. They have a firing range, and they're gonna let us use it.
And while Grant gets ready for action, Tori and Carrie prepare to get the results down on paper.
We need to find out whether or not these bullets are curving, but in order to do that, we need to be able to track the path of our bullets. So we've set up 5 frames of paper down the gun range 8 feet apart. That way when the gun goes off, the bullet will punch a hole in each one of those sheets of paper. Science is body. Now, the bullets are flying straight. Those holes should all line up. We should be able to see that by pointing a laser pointer down the hole.
Hey, it works!
Now, if those holes are not lining up, then we're curving bullets.
So the first test up is at regular human speed. Now I know we've already done this test ourselves, which qualifies as human speed, but the robot is capable of perfect execution. And that's what we need to do, is take out any differences in our timing or our aim and do it perfectly. Normally here at MythBusters we're pretty safety conscious, but on this experiment in particular, because we've got a gun going a full 360 degrees around, we have an extra set of precautions. Exhaust valves, open, open, open. Check. And because Tori and I are going to be in the danger zone here, we're wearing full bulletproof right here.
Turn elbow to hum.
Pin is in.
Trigger cylinder is out.
You ready to load the gun?
Almost.
Check.
10 more steps.
Damn.
Secondly, I've got a 25-point checklist to make sure that we can load and discharge the weapon safely. Okay,
Flies down.
check. And when we load the weapon, we've got this safety tape right here to keep us out of the horizontal plane. And finally, we've got a full wall of ballistic shields closing off that entire side of the range from this weapon. That ought to cover it.
Here we go. We are loading the gun. All right, we are loaded and hot.
Okay, pull the elbow pin,
Pin pull.
pressurizing the shoulder.
It's ready to go now. Ready?
Ready.
Take the pin pull. Let's go.
Get out of here.
With Grant's 25-point plan complete, the gunslinger is locked, loaded, and ready to unload.
Okay, this is going to be human speed.
Here we go. 3, 2, 1.
Nice.
Check it out.
Good shot. Let's go see if we curved that bullet.
I can see 2 and 3.
Remember, if the bullet did curve,
Fourth, we got all 5 frames. That was a good test.
the holes in the 5 sheets of paper, the physical evidence of the bullet's trajectory, won't line up.
Here's the laser, and lined with the hole. Can you see it all the way?
Science is so unforgiving. The bullet didn't curve. We can see the laser down at this end.
Straight shot at human speed. Now for us, this can confirms that human speed is not going to curb a bullet. We did it ourselves, we tried it with the robot, now it's time to ramp it up and see if superhuman strength is going to curb it.
Okay, so you saw it. They got, I got 10.8 inches, right, of lateral displacement. 10.8 inches with my best guess assumptions, observing their apparatus, and they got no lateral displacement. In fact, my the smallest it could possibly be would be 0.72 inches, and that's highly unlikely because I doubt they're shooting a bullet at 4,000 feet per second. So why did they not show any lateral displacement? Well, here are a few of the ideas I came up with. Maybe when the MythBusters measured the lateral displacement, she was actually angling the laser pointer, right? So she wasn't correctly pointing the laser pointer, so it didn't pick up on the lateral displacement. So that's idea number one. Idea number two, I can't imagine though the experimental error would be so high, is maybe the thing stopped at the instant the bullet was fired. I don't know. It didn't look that way, but that's a possibility as well. Three, there should be some natural curvature of the bullet because it is spinning. It doesn't spin really, really fast. And I wouldn't expect any sort of a curvature due to just the spinning of the bullets, or something called the Magnus force, anywhere near like 10.8 inches. So I don't think the fact that it's spinning, and you do have another force called the Magnus force that could possibly offset 10.8 inches. I think that's extremely unlikely. So I'm kind of at a loss why I got 10.8 inches is the most likely displacement, and they got 0. And as you saw, they could have measured, they could have easily measured a 3/4 of an inch displacement if they were doing the measurement correctly. So I don't know. I mean, I feel confident in the physics here. I think they blew it on this one. I'm just not sure how they blew it. So anyway, I hope you enjoyed that. I hope that was of some benefit to you. Have a good day. Thanks for watching. Bye-bye.